Okay, people, we are going to start the class. I'm going to share my screen. I'm going to share my screen now. Share sound. All right. I think I'm sharing already. I'm going to make sure I'm sharing just correctly. Right, so we are going to be focusing on more of the terms of electricity. So let me grab my material. Give me a moment. Okay, so we were discussing various terms of electricity on the last class. So let me just grab my material. We were discussing some numbers. Okay, we were discussing the numbers and forming the numbers. So in electricity, we have some measurements. YouTube electricity measurements. So as for electricity, we have different terms for electricity. Let's watch a video first, and then we move through some measurements for the electricity measurements. That's bad written. Ahí está mal escrito, es measurements con E. Okay.
So when you get your home energy bill, it lists the usage in kilowatt hours. But when you go to the store, you'll see things like 12-watt light bulbs, 9-volt batteries, and vacuum cleaners with 15 amps of sucking power. But what do these numbers even mean? I mean, why do we have so many different units to measure something that seems as straightforward as electricity? Surprisingly, the answer isn't just so appliance companies and physics professors can confuse you. It's because several important things have to happen in an electrical circuit for electricity to flow and for work to be done. You can think of a circuit kind of like the faucet on your kitchen sink. If you want water to come out, you need two things. You need the water itself and some pressure to force it through the pipes out your faucet and into your neti pot. Similarly, an electrical circuit uses electrons to carry the electricity, kind of like the water in our faucet analogy. But those electrons need something to push them along a circuit. This electrical pressure is what we call voltage and is often provided by two terminals, one with a positive charge and one with a negative charge. So on a battery, electrons flow from the negative end through whatever it is you're trying to power and then into the positive end, where they'll stay unless your battery is rechargeable. If you're plugging something into the wall, this voltage is instead provided by your power company. And although voltage just measures how strongly electricity is being pushed through a circuit, it's important because many circuits are designed only to accept a certain number of volts, which is why the hairdryer you bought in Monaco might release magic blue smoke if you plug it in New York. So now that you know what volts are, what about amps? Well, in this context, amp isn't short for amplifier, but rather for ampere, which is a unit of how much electrical charge is flowing past a given point in 1 second. So when you put volts and amps together, you can tell how much current is flowing and how hard it's flowing. Multiply these numbers and you get, finally, our third unit, the watt. Let's go back to our water analogy for a second. Let's suppose you wanted to spin a small water wheel because you just like watching things spin, or I don't know, maybe you have it hooked up to a generator. Let's say you have a really powerful water pistol that forces water through a tiny nozzle. Even though the small nozzle means the total volume of water flowing per second isn't all that much, you wouldn't want to fill your swimming pool with it, the high pressure creates a strong jet that can spin the wheel easily. But suppose instead of a water gun, you have a much wider hose that doesn't push the water out nearly as strongly, but because the hose is a lot wider, more water flows per second overall, and the wheel ends up spinning at the same speed it did with your water gun. If we think of the hose and the water gun pushing out electricity instead of water, we could say that they're delivering the same number of watts. For a more practical example, let's say you have an 1100 watt power supply for your computer that's drawing full load because you're rocking 4-way SLI or something. So if you plug that into a standard 110 volt North American outlet, some simple math tells you that 10 amps of current is running through your power supply. But if you take that same power supply and use it with a 220 volt European outlet, you're only drawing 5 amps. But since the amount of power in watts is the same, your computer will work just fine in both places, even though you're using different volts and amps. Well, that makes sense, Linus, but why the heck then is my energy bill in kilowatt hours? Is that a unit of time? No, actually, scientists are just mean. It's a unit of energy. Watts and kilowatts express how much energy is consumed per chunk of time, something scientists call power, which is not the same as energy. But if you multiply a kilowatt by an hour, the units cancel and you're left with a number that shows how much energy that you hogged by running your air conditioner, gaming rig, and novelty lava lamp all at once. But what if you're more concerned about battery capacity instead of what's coming out of your walls? Well, if you're buying a replacement battery or a battery pack, you might see their capacity listed in milliamp hours, again, not time. Doing the math shows that this is a unit of charge, not energy or power. So going back to our water example, this is like how much water you have in a bucket, not how much is flowing or how fast it's flowing. So a bigger bucket means you could charge your phone more times, and you can learn more about that and battery banks in this video here. So go forth then with your newfound knowledge and expertly buy the right voltage adapter, install the correct power supply, or just ace your electrical engineering exam if you want to do more with your life than work for some second-rate YouTube channel. But, what? Hey John, second-rate YouTube channel? Like, is that supposed to be a joke? It's not funny. Speaking of things that are no joke, TunnelBear VPN lets you tunnel through up to 20 different countries, well, one at a time, but allowing you to browse the...
So the main part for this are the three categories that we have for voltage, amperage, and ohmage, or resistance. So I'm looking for the, well, I'm going to find the Ohm's law. So in electricity, we have the Ohm's law that is going to be the tool to represent how the current is going to flow, how the voltage is going to be, and how the resistance is going to resist in a circuit. We have this, well, this is in Spanish, this is in English. Well, take a look at this. So as for this, we have Ohm's law, okay, for the electric current. Electric current is that's going to mean the flow of electrons, okay? Flow of electrons. And we have also voltage and resistance. So this is important because we need to focus on how this reacts in a circuit, and this is all mathematically explained. Esto pues es matemáticamente explicado de cómo funciona en un circuito también. ¿Ok? Por ejemplo, las pistolas, ¿verdad? Las pistolas taser que se usan para, ahí sí que para inmovilizar a las personas, tienen su principio de operación al final, pues eléctrico en Ohm's Law, ¿verdad? En la ley de Ohm. Muchas de las cosas que se utilizan al final siempre van a tener esa esa manera, ¿verdad? De cómo representarse por la ley de Ohm. We have current here, current, voltage, and resistance. Electric current, voltage, and resistance. We have also another measurement for the watt, for the power. I'm going to put this bigger. Voy a poner esto más grande. So we have another measurement that is the power. Power is going to mean how much of that load is going to consume electricity. La potencia en watts es cuánto se va a necesitar para que el circuito funcione y que la carga esté en operación, ¿verdad? Aquí sí ya entran cosas como la carga, y no la carga eléctrica, sino que carga se le llama a qué me va a consumir más. Por ejemplo, un set de motores, donde yo tengo algo muy específico, ¿verdad? Que debe operar. Por ejemplo, si es algo como un microondas en una casa, ahora va a necesitar 1500 watts para operar. Esa es la potencia que necesita para lo que es necesario. Y pues de ahí va a ir decrementando algunas cosas y va a ir incrementando, por ejemplo, a lo que son motores, ¿verdad? Generadores diésel. Es entre más pequeña el consumo eléctrico, pues significa que no va a estar consumiendo tanto de la fuente de energía. That's the meaning of this. So power is going to equals the voltage multiplied by the intensity or the current. We also have the resistance multiplied by the current 2 times. Voltage 2 times divided the resistance. So that's for the power. As for the voltage, take a look at this. We have resistance multiplied by current. Current, recordemos, current es la intensidad. Resistance, la resistencia. Power, ¿verdad? La potencia, y voltage, el voltaje. Ya vimos la de poder, la de la potencia. Bueno, a veces esto se pone como incorrectamente como poder, ¿verdad? Porque power también es poder, pero nosotros en electricidad, pues al final sabemos que debe ser potencia, ¿verdad? Potencia. That's the intensity for this. This is la intensidad, current, resistance, and voltage. So for the voltage, we have resistance multiplied by current. Okay, current. Current is going to mean the E. Okay, current. Voltage, I think that's pretty self-explanatory. Es bastante explicativo esto del voltaje, ¿verdad? Con V voltage. V voltage, current, that's going to mean the I for current. No E. E en español, ¿verdad? R, that's meaning the resistance. Okay, for the voltage, resistance multiplied by intensity, by current. Or power divided by the current. Or square, the square of the power multiplied by resistance. That's the square, right? Square. As for resistance is going to involve voltage divided by intensity. How much I'm going to resist to these measurements. La resistencia es el voltaje dividido la intensidad, significando cuánto le voy a poder resistir, ¿verdad? A lo que es estas medidas de voltaje y de intensidad. O sea, las resistencias van cambiando en su capacidad, ¿verdad? En circuitos digitales, pues son unas pequeñitas, ¿verdad? Que tienen unas bandas con colores. ¿Okay? Ya en circuitos más grandes, pues llegan a tener también la manera de bobinas, ¿verdad? Como bobinas, como la impedancia. Para la resistencia, o sea, es el opuesto de la resistencia, la verdad, la impedancia. Okay, so for the resistance, I have voltage divided current. As for this, I have voltage 2 times divided power, potencia, ¿verdad? Or I have power divided current 2 times the current, okay? Tengo aquí unas ecuaciones, ¿verdad? De cómo se va a reflejar la resistencia involucrando la potencia. Then I have current. Current, that's going to mean the flow of electrons in a medium. Okay, so as for this, we have the square of the power divided resistance. Divided, right? Dividido, divided. Multiplicado, multiply. Or by. I also have the other option to form it like the power divided the voltage. Power divided voltage. Or voltage divided the resistance. So for me, something that is pretty easy to remember is voltage. Voltage is the resistance multiplied by the current. Voltage is the resistance multiplied by the current. So that's like the easiest form for me. Esa es la manera más fácil de la que yo recuerdo siempre la ley de Ohm. Right? Voltaje es proporcional a la resistencia por la intensidad. So that means that this has to change in order to supply the correct voltage. De que esto debe ir cambiando si yo tengo una carga muy grande, ¿verdad? Tengo una carga muy grande, el voltaje también debe ser grande. ¿Okay? La intensidad puede variar también, pero esto como es un por, ¿verdad? Pues si no tengo mucha resistencia, el voltaje también se va a ir para arriba. Cuando tenga mucha intensidad, se va a ir para abajo, ¿verdad? Si esto se acerca a cero, sea lo que sea por cero, va a ser cero. Si se acerca mucho a cero, la intensidad va a empezar a bajar por la multiplicación, ¿verdad? Porque, por ejemplo, que tuviéramos 1 acá de intensidad por cero, completamente cero. Pero si tenemos 0.1 por 1, ¿cuánto es eso? 0.1 por 1. Déjenme traer por acá la calculadora para hacerlo aquí en la pantalla. 0.1 por 1. 4 está bueno. ¿Okay? Entonces va a empezar a bajar. Va a empezar a bajar todo lo que es el voltaje. Por la resistencia. Porque ese es el resultado de una multiplicación. ¿Ok? Así que de nuevo, voltaje va a ser igual a resistencia por intensidad o las diferentes formas. Ustedes también podrán tener su forma en la que les gusta más recordarlo. Algunos lo recuerdan por la ley de Ohm. Algunos por lo de intensidad. Intensidad es igual a voltaje partido a resistencia. Y todos esos se van complementando de circuitos muy pequeños, ¿verdad? Como un carro ahí de baterías. ¿Verdad? Un carro ahí muy feo. O hasta pues unos tendidos eléctricos enormes de miles y miles de watts, de voltios. Ok.
One of the most useful ways to analyze a circuit is to look at the relationship between voltage and current. And there is one component that makes that analysis very simple. This is the resistor. Its function is very simple. It restricts the flow of electrons. Now, impeding current may seem a little silly, but there are times you may want to reduce the current flowing to that analysis very simple. This is the resistor. Its function is very simple. It restricts the flow of electrons. Now, impeding current may seem a little silly, but there are times you may want to reduce the current flowing to a component or lower the voltage going to some sensitive electronics. In an ideal world, the resistor creates a linear relationship between current and voltage. And if you know two of those three things, voltage, current, and resistance, you can easily calculate the third. We'll see how to do that later, but for now, let's see how a resistor works in a circuit. In the previous episode, I showed how moving current can be represented by steel balls in a tube. If one steel ball represented one electron, then it would take around 6.25 times 10 to the 18th steel balls to move past a point per second to make 1 amp. Since I don't have billions of steel balls in a massive plastic tube, we need some other way to show electric current. As it turns out, fluids like air and water actually make a pretty good representation for electric current. What I've got here is a circuit, not of electricity, but of water. I've added some mica powder and blue food coloring to it so you can see the water flowing more easily. In our little demo, the pump represents a power supply like a battery or a wall adapter that pulls water up from a well and gives it the push needed to move a circuit. The tubes are like wires. They provide a path for the current. The water pressure in the tubes corresponds to voltage, and the amount of water moving through a tube corresponds to electrical current. Note that we're using conventional current, so the water is flowing from high pressure to low pressure. Amperes is coulombs per second, so in terms of water, that would be volumetric flow rate, something like our analogy of a resistor. This is some steel wool shoved into a tube. You can see how all that material resists the flow of water, and there is higher pressure on the side the water is entering the resistor. The same holds true in electronics. There is a voltage difference between the ends of the resistor when current is flowing through it, and this is known as a voltage drop. Let's go back to the actual resistor component. If you were to slice one open, you would find coils or film of tiny wire or a solid core made of a carbon mixture. However it's made, the resistor acts to impede current. In 1825, the German physicist and mathematician Georg Ohm began experimenting with early chemical batteries and thermocouples to produce voltages. By varying the size of wires used to complete the circuit, he determined that voltage and current were proportional. In math terms, that means the voltage between 2 points is equal to the current flowing between those points times some number, and that number is known as the resistance between those points. Ohm's law is often written as V equals IR, or voltage is equal to current times resistance. Lucky for Mr. Ohm, the unit for resistance was named after him. The ohm is abbreviated with the Greek letter omega. With this information, we can begin to analyze circuits. As an example, we'll connect a resistor to a power supply that provides 3 volts. The electronic symbol for a resistor is a zigzag with 2 terminals. It represents a more complicated path and therefore reduced current flow. Note that it doesn't matter which way we connect the resistor, it will do its thing regardless of orientation. We will connect the terminals of the resistor to the positive and negative terminals of a power supply that's been set to act as a voltage source. A voltage source, similar to a battery, will supply as much current as needed to maintain a particular voltage between the terminals. Now that we have a circuit, current will flow from the positive terminal of the voltage source through the resistor and back to the negative terminal. The power supply will be set to 3 volts, and it will also tell us how much current it is supplying. With that information, we can determine the resistance of the resistor. Let's try it. All right, I've connected the resistor to this power supply using some alligator clip leads. You'll notice I used red for positive and black for negative terminals connected to the power supply. When I turn it on, it reads about 3.03 volts. And it also tells me that about 0.03 amps are flowing from the positive terminal through the resistor and back to the negative terminal. Let's see if we can use this to calculate the resistance of this component. Using Ohm's law, V equals I times R, we can plug in the values from our readings. So 3 volts equals 0.03 amps times R. Using a little bit of algebra, we can calculate R. And we get R equals 101 ohms. Now that we've mathematically determined that we have a 101 ohm resistor, let's check our work. This is a digital multimeter, and it's one of your best friends when analyzing a circuit. Most basic models can do things like measure voltage, current, and resistance. We'll set this one to measure resistance and touch the leads to the ends of the resistor. As you can see, it's reading about 100.2 ohms, which is pretty close to our math results. Since this is labeled as a 100 ohm resistor, we'll call it good enough. If you're wondering why the measurements and calculations didn't come out to be exactly 100 ohms, that's because there are inconsistencies in the manufacturing of resistors, which of course means that the resistance can be a little bit off from the listed value. Additionally, there's resistance in the wires and potentially the power supply itself, so measuring the voltage between the terminals of the power supply could be a little bit different than measuring the voltage between the terminals of the resistor. Back to our water demo, we see that the steel wool, much like the resistor, restricts flow. If we were to add an even denser material like a sponge, the water flow would decrease even further. The same holds true in electronics. For a given voltage, as resistance increases, current decreases. Knowing Ohm's law by heart, V equals IR, will get you through many troubles in the electrical world, so it's one of the few equations I recommend committing to memory. Besides, it's only 3 letters. As it turns out, by resisting current, electrical energy gets converted to heat. In the next episode, we'll learn how to calculate electrical power and figure out how to do something useful with all of that heat from resistors.
Okay, so pretty good explanation. As for how we use these words, we are going to do a word search. Vamos a hacer una actividad de la sopa de letras para afianzar estos términos. Se los voy a enviar por acá. Para que lo podamos trabajar. I'm going to give you 5 minutes. To complete that.
Okay, let's continue. We already saw some of the words there. Ya vimos una de las palabras ahí. Let's continue and do the pronunciation. Pronunciation for the words of the word search. So let me put the word search here. All right. So we have some words here.
I'm going to pronounce and you can repeat. Resistance. Resistance. Amperage. Amperage. Ese va más como así, amperage, así junto, amperage. Heat. Heat. Resistance, resistance, amperage, heat, current, current, flow, flow. Esto, el que es el multímetro, multimeter, 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 multimeter. El multímetro, ¿verdad? Multimeter. Capacitance, capacitance. Voltage drop, voltage drop. Bueno, vamos hacia la A para hacer voltage drop, ¿verdad? Wire, que es cable. Ah, bueno, no les he dicho en español. Resistance, resistencia. Amperage, amperage, miren cómo es. Amperage, amperage. Heat, heat, calor. Amperaje, resistencia. Current, corriente. Current. Flow, flow. Como la música, ¿verdad? Flow, sí, es el flujo. Flow. Multimeter, multimeter. Multimeter. Multímetro, capacitance, capacitancia, voltage drop. Voltage drop es la caída de voltaje. Wire es cable. Wire es cable. Measurement, measurement. Measurement significa medida. Measurement. Measurement. Circuit. Circuit, circuito. Miren, para esa, cuando lo quiero pronunciar, circuit, ya no digo la U. No digo circuit, ¿verdad? No. Circuit. 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 Y con K, ¿verdad? Más hacia la K. Circuit. Direction. Circuit, circuito, measurement, medida. Direction, dirección. Increase. Es el incremento. Increase, ¿verdad? Incremento. No se mira mucho ese color. Increase. Decrease, el decremento. Decrease. Ok, yo voy a hacer una grabación de las palabras para que la puedan tener ahí de ejemplo, ya que la actividad es grabar. Un audio, la actividad. Completar sopa de letras y colocar captura. Y para el audio, grabar un audio con las palabras de la sopa de letras. ejemplo y les voy a poner por ahí el audio que voy a grabar ahorita. Resistance, amperage, heat, current, flow, multimeter, capacitance, voltage drop, wire, measurements, measurements con muchas medidas, measurement, circuit, direction, increase, decrease. Right. Lo voy a poner por acá. Y lo voy a poner aquí para que lo escuchemos. Está compartiendo el sonido. Resistance, amperage, heat, current, flow, multimeter, capacitance, voltage drop, wire, measurements, measurements con muchas medidas, measurement, circuit, direction, increase, decrease. Okay, so that's the audio. Ese es el audio. Así que voy a ponerle 5 minutos para que puedan hacer ese audio. Okay, let's continue. We are going to review the words. Repasemos las palabras una última vez. Resistance, resistance, amperage, amperage, heat, heat, current, current, flow, flow, multimeter, multimeter, capacitance, capacitance, voltage drop, voltage drop, voltaje va a ser así, voltage, con che, mucha che, voltage, voltage drop, no es voltage para nada, no con nada, sino que va con I, voltage, voltage drop, wire, wire, measurement, measurement, circuit, circuit, direction, direction, increase, increase, decrease, decrease, incremento, decremento. Eso significa ese increase y decrease. Increase, decrease. All right, let's continue. So let's review the Ohm's law quickly. So just to finish with this subject, and you are going to do some exercises. Vamos a repasar esto y van a hacer unos ejercicios. Pues, ¿qué es lo que necesito siempre? Necesito saber dos parámetros siempre de la ecuación, ¿verdad? Siempre voy a necesitar dos valores. No puedo hacer nada si no tengo dos valores. Así que son tres valores los que se tienen, ¿verdad? La parte más sencilla para mí es la de voltaje es igual a resistencia por intensidad. Esa es como la forma más fácil para mí de recordarlo. Pero obviamente necesito tener esos dos valores, si no, no voy a poder trabajar. Siempre necesito dos valores para trabajar. Eso es obligatorio, ¿verdad? Ok, así que les voy a colocar un video donde pues ya va desarrollando un poquito más la ley de Ohm, porque vamos a hacer varios ejercicios que les en donde van a poder ustedes aplicar las ecuaciones. Así que pensando en la ecuación esta, pues siempre igual, siempre despejando, ¿verdad? Siempre despejando. Si yo quiero despejar voltaje, ¿verdad? ¿Qué es lo que voy a tener acá? Voltaje, ¿verdad? Suponiendo cuál ¿qué letra quiero despejar primero? Por ejemplo, que tengo esta de voltaje es igual a I por R. Suponiendo qué es lo que voy a despejar primero, por ejemplo, que quiera intensidad, ¿sí? Pues tengo que dividir intensidad acá y divido intensidad acá. Entonces el resultado, por ejemplo, resistencia, cuando tengo resistencia, ¿verdad? Es igual a voltaje dividido intensidad. Porque ya despejé resistencia, ¿no? Que sería esta, ¿eh? Voltaje dividido intensidad. Pero todo sale del VIR, ¿verdad? Voltaje es igual a intensidad por resistencia. De ahí yo puedo despejar lo que sea. Siempre cuando tenga los dos valores, pues ya los voy a poder aplicar.
Pipes out your faucet and
Eso es lo que estábamos viendo la otra vez. Y esa es la que quería.
In this video, we're going to talk about Ohm's law. So what is Ohm's law? Ohm's law describes the relationship between voltage, current, and resistance. Perhaps you've seen this equation. V is equal. In this video, we're going to talk about Ohm's law. So what is Ohm's law? Ohm's law describes the relationship between voltage, current, and resistance. Perhaps you've seen this equation. V is equal to I times R. V stands for voltage, I stands for the current, R is resistance. Voltage is measured in the units volts. I, which represents the current, is measured in amps. And R, the resistance, is measured in ohms. Now, you need to know that as the voltage in a circuit increases, the current will increase, provided that the resistance stays the same. If the resistance goes up, the current will go down if the voltage is held constant. So voltage and current, they're proportional to each other, and resistance and current, they're inversely related to each other. Now let's work on a practice problem. Let's say if we have a 12-volt battery connected across a 4-ohm resistor. What is the current flowing in this circuit? Conventional current flows from the positive terminal of the battery to the negative terminal of the battery. This is the opposite direction to electron flow. So to find the current in this circuit, we can use Ohm's law. V is equal to IR. So the voltage is 12. We're looking for the current. The resistance is 4. So we need to solve for the variable I. Let's divide both sides by 4. 12 divided by 4 is 3, so the current is going to be 3 amps. Now let's say if we have 3 resistors connected in series, like this. Let's say this is R1, R2, and R3, and it's connected across a 60-volt battery. Now let's say that R1 has a value of 3 ohms, and R2 is 4 ohms, and R3 is 5 ohms. So what is the current flowing in a circuit? In order to find a current flowing in a circuit where the resistors are connected in series, you need to find the total resistance. And the total resistance is going to be R1 plus R2 plus R3. You just need to add the values of the 3 resistors. So 3 plus 4 plus 5, that's going to give us 12. So the total resistance in a circuit is 12 ohms. Next, you need to calculate the current. So we could use the formula V is equal to IR. So V is 60. That's the voltage across the 3 resistors. We're looking for the current, and then the total resistance is 12. So you can treat this as if it's one big resistor, and you have a 60-volt battery source across a 12-ohm resistor. What is the current in that resistor? So what we need to do is divide both sides by 12 to get the current by itself. 60 divided by 12 is 5. So we have a current of 5 amps flowing in this circuit. Now, once we have the current, we can calculate the voltage drop across each resistor. What is the voltage drop across the first resistor? Now, in this series circuit, the current that flows in a circuit is the same as the current flowing through R3, R2, and R1. Because there's only one path for the current to flow, it's going to be the same, 5 amps. So to find the voltage across the first resistor, we can use the current that flows through the first resistor times the resistance value of that resistor. So we're using Ohm's law, but in a different way. I1 is going to be the same as I, because that 5 amp current is flowing through each resistor. But R1 is different. R1 is going to be 3. So it's 5 times 3. So we have 15 volts across R1. Now what about across R2? What is the voltage across R2? Well, we could follow the same pattern. So we could say V2 is equal to I2 times R2. So the current is still going to be 5 amps, but this time the resistance is 4 ohms. So 5 times 4, that's going to give us 20. So we have 20 volts across R2. Now across R3, it's going to be V3 is equal to I3 times R3. So I3 is going to be the same as I2 and I1, so that's 5 amps. R3 is 5, so 5 times 5 is 25. So notice that if you add up 15 plus 20 plus 25, it gives you 60. And so the voltage of the battery is equal to the sum of all of the voltage drops across those resistors. And there's something called Kirchhoff's voltage law, which basically states that as you go around a circuit in a loop, the total voltage will be 0. And it makes sense because the battery, it increases the energy of the circuit because it supplies energy to the circuit, so it increases it by 60. The resistors consume energy from the circuit, so they decrease it, thus they have a negative value. So if you add up positive 60 with negative 15, negative 20, and negative 25, you get 0. Because the energy that flows into a circuit must equal the energy that comes out of the circuit. Thus, Kirchhoff's voltage law. It always applies whenever you have a closed loop. So the sum of all the voltages in a closed loop will always add up to 0. Now what's going to happen if we connect 3 resistors in a parallel circuit? Let's calculate the current in such a circuit. In a series circuit, the current flowing through the resistors that are connected in series is the same, because the current only has one path in which it could flow. In a parallel circuit, the current has multiple paths, and so it could vary. However, notice that whenever resistors are connected in parallel, the voltage across those resistors is the same. So let's say if we have, in this case, a 12-volt battery. Each resistor is connected across that 12-volt battery. And so all of them have 12 volts across their terminals. So let's call this R1, R2, and R3. And so let's say that R1 has a value of 3 ohms, and R2 is going to be 4 ohms, and R3 is going to be 6 ohms. What is the current flowing through each resistor? So we can use this formula. V1 is equal to I1 times R1. So remember, in a parallel circuit, the voltage across the resistors connected in parallel is the same. But in a series circuit, the current flowing in this case, V1 is 12 because we have 12 volts connected across R1. And to find the current flowing through this resistor, we need to use that formula. R1 is 3, so the current is going to be 12 divided by 3. So we have a current of 4 amps flowing through R1. Now let's do the same for R2. So let's use the formula V2 is equal to I2 times R2. It's basically Ohm's law, but with different subscripts. So V2 is still 12, and R2 is now 4. So it's going to be 12 divided by 4, which will give us a current of 3 amps. Now to calculate I3, it's going to be 12 divided by 6, following the same pattern, and so that's a current of 2 amps. Now, notice that as the resistance increases, the current decreases, as we mentioned in the beginning of this video. Here, notice that R1 has the lowest value, and it has the highest current. R3 has the highest value, but it has the lowest current. So as you increase the resistance, the current decreases. If we increase it to 6, the current decreases to 2. And if we decrease the resistance, the current will increase. If we decrease it to 3, the current goes up to 4, provided that the voltage is held constant. And so you'll see this relationship in a parallel circuit, as you can see it here. Or in a series circuit too. You can see that relationship there as well. Now, what is the current that leaves the battery? how can we determine the current that's leaving the battery? The total current in the circuit, which we'll call IT, that leaves the battery, is going to be the sum of the individual currents. So it's going to be 4 plus 3 plus 2. 4 plus 3 plus 2 is 9. So the total current here is 9 amps. Now let's focus on this point. What is the current that is flowing through that branch? Right here, along, let's say, this wire. What is the current in that region? So now we need to use something called Kirchhoff's current law. We saw in the last example that Kirchhoff's voltage law, which basically states that the sum of all the voltages around the loop adds up to 0. Well, Kirchhoff's current law is very similar. The current that enters the junction is equal to the current that leaves the junction. Now let's draw a picture. So we have 9 amps of current flowing to this point, and we have 4 amps that's leaving it. Now the current that is flowing to a junction must equal the total current that is leaving a junction. So we have to have current leaving in this direction, and it has to be 5 amps because 5 plus 4 is 9. So we have a total of 9 amps of current that enters this junction and 9 amps of current that leaves it. And so that's the basic idea behind Kirchhoff's current law. So we have 5 amps flowing to the right in this direction. Now out of those 5 amps, 3 amps is going this way. So that means the other 2 amps flows in this direction. And you can see how it's like a river splitting off into 3 directions. So in this section, we still have 2 amps of current that's traveling here. And then when it joins up with a 3 amp current, 3 and 2 will add up to 5. And so we have 5 amps flowing in this region. And then the 5 and 4 will get together. And so we're going to have a total of 9 amps of current flowing in this region. And so as you can see, the current that's going this way is going to be the same as this current here, 9 amps. And so hopefully this all makes sense. And so I want to give you a basic idea of how to use Ohm's law in a simple circuit, in a series circuit, and also in a parallel circuit. So that's it for this video. Hopefully you found it to be helpful, and it gave you a good understanding of Kirchhoff's voltage law and his current law as well. Thanks for watching.
Okay, people. So as for this, the video showed how is current going to perform in series circuits and in parallel through Kirchhoff's law. En español le dicen la ley de Kirchhoff, la ley de Kirchhoff o las mallas de Kirchhoff, en cómo la intensidad aquí se va a dividir entre cada uno de los resistores y la resistencia acá es la total, pero ¿qué es lo que va a pasar? El voltaje se va a dividir, así que va como en opuesto, ¿verdad? Hacia acá se va a dividir el voltaje entre cada resistor y va a permanecer la intensidad fija, y acá en la malla de Kirchhoff va a ser la intensidad la que va a ser dividida y el voltaje se va a mantener. Entonces es como la
Provided
meta
that
completa.
the voltage is held constant.
All right. So we are going to do some exercises. Voy a poner unos ejercicios. Es un PDF que tenemos que hacer. Es de la ley de Ohm. No llegan a profundidad como lo que es las mallas de Kirchhoff, pero no, sino que quiero que empleen un poquito del conocimiento ahí de la ley de Ohm básica, y lo pueden hacer en diferentes, pues desde hacerlo en Word hasta hacerlo, algunos tienen ya programas o sea, tienen aplicaciones que pueden escribir sobre el PDF en su teléfono y también pueden hacer capturas y escribir con el Telegram encima. El Telegram les permite a ustedes escribir cuando van a editar, le pushan ahí para el texto y pueden hacerlo, ¿verdad? Esa es la manera en que, o sea, media vez lo entreguen, hasta si quieren imprimirlo, ¿verdad? Si les queda fácil imprimirlo y hacerlo a mano, igual, no hay problema. Ustedes pueden hacerlo. Les voy a mostrar el primero. Ok, that's the Ohm's Law worksheet. Tenemos nombre, la fecha, ¿verdad? Que esto es del 2018 esto. De periodo no, solo su nombre acá. Y tenemos un pequeño recordatorio. We have a reminder of Ohm's Law. Voltage is going to equal current times resistance. Voltaje va a ser igual a lo que es intensidad por resistencia. O bien, despejando cada una de estas, pues ya puedo tener la resistencia va a ser igual al voltaje dividido en intensidad, o la intensidad va a ser igual al voltaje dividido a la resistencia. Van siempre correlacionados, ¿verdad? Ok. Right. Show all your work, have the correct units, and circle your answer. Bueno, lo que tengo que hacer, por ejemplo, for the first one, what is the current in a 160 volt circuit if the resistance is 2 ohms? 2 ohms. Okay. What is the current in a 160 volt circuit if the resistance is 2 volts? So what I need here, I'm going to do the example. Okay, is to find out two values. I have 2 ohms here. 2 ohms, and I have the voltage, 160 volts. And I need the current. For this one, I need the current. So what's the way I can get the current? The equation is going to be voltage divided by resistance. That means 160 volts divided 2 ohms. All right. So what is happening there is that I have 80 amperes or 80 amps. Okay. Voltage divided resistance. 100 divided 160 divided 2 for the 80 amperes or amps. Si luego quiere decir amperes, puede ser amps. 80 amps, I'm sorry. 80 amps. So 160 volts, 2 ohms, 160 volts divided 2 ohms, 80 amps. Okay, this is the first one. Este es el ejemplo. Les voy a tomar una captura a esto. Y así pueden continuar con lo demás. We are going to have 15 minutes for this. Hay varios aquí. Así que vamos a tener más tiempo para eso cuando finalice ahí la clase. Okay. Now let's continue. Now that we have electricity on the Ohm's law, let's do a power exercise. What is power? Ya que tenemos los conceptos básicos de electricidad, ahora vamos con la potencia, power. What is power? Power factor, AC, DC, fuses. What is electricity?
Today I'm going to talk about watts and electrical power. In my previous video about voltage, I talked about how amperes is the number of coulombs flowing per second, and volts is the number of joules of energy transferred for each coulomb of charge that flows. I had an example set up where I had a power supply connected to a motor, and because I had 1.8 amps flowing, and for every amp 1 joule was being delivered, this meant that 1.8 joules per second was getting delivered to the motor. This is what electrical power is. Power is the rate at which energy gets supplied or used up. Instead of constantly saying joules per second, we have a unit that we use for power, called the watt. 1 watt is equal to how amperes is the number of coulombs. Today I'm going to talk about watts and electrical power. In my previous video about voltage, I talked about how amperes is the number of coulombs flowing per second, and volts is the number of joules of energy transferred for each coulomb of charge that flows. I had an example set up where I had a power supply connected to a motor, and because I had 1.8 amps flowing, and for every amp 1 joule was being delivered, this meant that 1.8 joules per second was getting delivered to the motor. This is what electrical power is. Power is the rate at which energy gets supplied or used up. Instead of constantly saying joules per second, we have a unit that we use for power, called the watt. 1 watt is equal to 1 joule being transferred per second. So for our example with the motor, 1.8 joules per second means that 1.8 watts of power are being delivered to the motor. If we increase the voltage to 2 volts, more current flows and more energy gets transferred for each unit of charge. So now we're getting 4 joules per second, or 4 watts of power being supplied to the motor. Since more work is being done per second, the motor spins faster. Now, in real life, no engineer is going to waste time converting volts into joules per coulomb and amps into joules per second. You can instantly calculate power with this very simple shortcut. Voltage times current equals power. Let's try this formula out with a real-life example. This is supposed to be a 40-watt light bulb, but I want to see how much power it's actually drawing in real life. I'm playing with high-voltage mains electricity here, so do not try to replicate this experiment at home. I'm using a standard North American wall outlet that supplies 120 volts, and my multimeter is showing that we have exactly 119.6 volts going to the light bulb. Now I'm going to switch my multimeter to measure current, and we can see the light bulb is drawing 337 milliamps from the wall outlet. So 119 volts times 337 milliamps means that this 40-watt light bulb is actually drawing 40.3 watts. So it's converting 40.3 joules of energy into light and heat every second. Now I want to really emphasize that it's voltage and current that leads to power. Voltage and current can be combined in different ways to get the job done. For example, you could design an LED lighting system that runs from 12 volts and make it so that it draws 10 times more current, and you'll still get the same 40-watt draw. And since LEDs are more efficient, you'll get more light from every watt. But not every situation is going to be better off with low voltage. For example, a high-powered robot might actually be more efficient with a higher battery voltage. Speaking of LEDs, in my previous video on basic electricity, we had an example with a low current, roughly 20 milliamps, flowing through a resistor and an LED. And the resistor got so hot that it went up in smoke. Now that we know about electrical power, we can explain why this happened. We know that voltage times current equals power. And from my previous video about resistance and Ohm's law, we know that voltage divided by resistance equals current. So let's substitute the current term in our power equation with Ohm's law and see what happens. Using a little algebra, you can see that another way to calculate power is voltage times voltage over resistance, or power equals V squared over R. This equation will let us find out the amount of power being delivered to a resistor when all we know is the voltage and the resistance. I was powering the system with 140 volts, and the LED had a 3-volt drop across it. So this meant that the resistor must have had 137 volts across it. The power being delivered to the resistor, in this case heat, is given by V squared divided by R. 137 volts times 137 volts divided by 6,800 ohms equals 2.76 watts of heat. The resistor I was using was only rated for 1/4 of a watt of heat, so no wonder it went up in smoke. If we wanted something that could handle the 2.76 watts of power, we'd need something a lot bigger, something that could dissipate more heat, like this resistor which is rated for up to 5 watts. Nearly everything in electronics will have a power rating, which basically means how much power can it handle before it goes up in smoke. As you learn more about electronics, you'll find that things like diodes and transistors will all have their power ratings listed in a datasheet. And of course, other things will have power ratings, like light bulbs, electric heaters, microwaves, and this refers to how much energy they're converting per second. Finally, I want to make something very clear. I've intentionally shown you a lot of high voltage examples because watching things catch fire is really fun, and I think it's a good way to visualize electrical power and what it can do. But at home, you don't need to have a large collection of big resistors like these in order to play with electronics. Most of the circuitry you play with at home will run off of low voltages, like 12 volts or less, and have low currents of a few milliamps. So simple 1/4 watt resistors like this are good enough for almost anything, as long as you pick the right resistance value. And by now, you should know enough about electricity to build some pretty cool things. Thank you for watching. Don't forget to subscribe and thumbs up, and check out the website if you've been enjoying this series on basic electricity.
All right, so that's the power explained as how the.
Now I'm going to switch my multimeter to measure current, and we can see the
I'm sorry. So how power is going to be that measurement of the load getting power from the power supply. A lot of power there. Así que la potencia va a ser esa medida de cómo se va a consumir, cuánto va a demandar, ¿verdad? La carga de lo que es la electricidad. Y hay diferentes tipos de cargas y hay diferentes niveles también de cargas. Aquí tenemos los ejemplos con bombillos o una luz LED, ¿verdad? Acá en el circuito. So for this electrical power is going to be proportional to the voltage multiplied by the current. Okay, power is in watts, voltage is in volts, and current is in amperes, and resistance is in ohms. Así que la potencia es cuánto se está consumiendo, ¿verdad? Del voltaje y de la intensidad dentro del circuito. Y nos sigue pues explicando todos los conceptos y de los diferentes resistores que hay. Y aquí hay una parte bastante clave de cómo funciona ya a un nivel. Un poquito más de cuánto van a consumir. Por ejemplo, una luz LED, incluso hay algunas de 6 watts ahora. Hay unas cosas así en cuestión de ahorrativas, ¿verdad? 6 watts y tienen una buena manera ahí de iluminar. Y de ahí tengo pues ya aparatos electrodomésticos más grandes. Por ejemplo, el microondas, que muchas personas a veces les gusta usar bastante microondas o en negocios usan bastante microondas y es bastante caro. 1200 watts, 1200 watts. For this, the heater, el calentador, 1500 watts, como una ducha también, ¿verdad? Que llega a ser bastante fuerte. Por eso a veces recomiendan no ducharse por tanto tiempo porque también los alambres llegan a calentarse, ya que hay mucha más electricidad siendo demandada en todo el circuito.
ratings, like light bulbs, electric heaters, microwaves, and this refers.
Y para muchos, por ejemplo, muchos inversores, pues yo tengo unos watts destinados a ese inversor. O sea, yo no puedo como que poner cualquier inversor. Le voy a poner por acá, power inverter. El principio de operación, ¿verdad? De cambiar de tipos de energía, de corriente alterna, corriente directa. Todavía no hemos visto la corriente alterna y corriente directa. Lo vamos a ver en este momento, pero los principios de operación, ¿verdad? Son de eso, ¿verdad? De cuánto va a poder aguantar. Por ejemplo, un inversor de carro a veces son de 700 watts, 750 watts. So let's take a look at the types of electricity. Types of electric current. We have DC and AC.
Previously, we talked about how electric charges can build up on surfaces and create something known as static electricity. In this episode, let's talk about what happens when these electric charges continuously move in a process known as current electricity. Most electronics, everything from your refrigerator to your smartphone, requires current electricity to operate. Let's assume that we have a copper wire that's filled with copper atoms. Copper is one of those elements that has only one electron in its outermost shell, which means that with only a little energy, that electron can be easily ejected. If we push a free electron into the copper wire, it will eventually find a new atom to latch onto. The negative charge of that electron will eject another electron from the outer shell, which will then move on to the next atom, and so on and so on. This chain of moving electrons creates a flow known as electric current. Some elements, like copper, aluminum, and gold, can move electrons easily and are known as conductors. We can look at moving charges in another way. Let's say that this tube is a conductive wire and the steel balls are negative electric charges, electrons in this case. We might think that one charged particle needs to move completely through the conductor to create a flow, but that's not actually the case. As we push a ball in one end, the force causes all the balls to move and one pops out the other end. As you can see, one electron, even if it doesn't move very far, can force all the other electrons to move, creating a flow. What we just showed was electric current, which is a flow of electric charge. In most circuits, this is accomplished by moving electrons. The unit for measuring current is the ampere, which is often abbreviated known as static electricity. In this episode, let's talk about what happens when these electric charges continuously move in a process known as current electricity. Most electronics, everything from your refrigerator to your smartphone, requires current electricity to operate. Let's assume that we have a copper wire that's filled with copper atoms. Copper is one of those elements that has only one electron in its outermost shell, which means that with only a little energy, that electron can be easily ejected. If we push a free electron into the copper wire, it will eventually find a new atom to latch onto. The negative charge of that electron will eject another electron from the outer shell, which will then move on to the next atom, and so on and so on. This chain of moving electrons creates a flow known as electric current. Some elements, like copper, aluminum, and gold, can move electrons easily and are known as conductors. We can look at moving charges in another way. Let's say that this tube is a conductive wire and the steel balls are negative electric charges, electrons in this case. We might think that one charged particle needs to move completely through the conductor to create a flow, but that's not actually the case. As we push a ball in one end, the force causes all the balls to move and one pops out the other end. As you can see, one electron, even if it doesn't move very far, can force all the other electrons to move, creating a flow. What we just showed was electric current, which is a flow of electric charge. In most circuits, this is accomplished by moving electrons. The unit for measuring current is the ampere, which is often abbreviated as amps and written with a capital A. 1 ampere is defined as 1 coulomb of charge moving past a point per second. Let's look at a cross-section of wire carrying an electric current. If it takes 3 seconds for 6 coulombs of charge to move through that cross-section, then we say that 2 amps are moving through that wire. Unfortunately, electric current doesn't just magically flow through wires. It needs a little help. If left alone, the electrons in a wire won't move. We need to give them a little push. To do that, we'll use a voltage source like a battery. In a battery, there is a buildup of negative charge on one side in the form of excess electrons. The other side has a buildup of positive charge, an absence of electrons in this case. The charges want to balance out, but the only way to do that is for the excess electrons to flow around the battery through a conductor that we provide. If we connect a piece of wire to the negative terminal, the electrons will push against the electrons in the wire. However, Air is an insulator as its molecules do not have very mobile electrons, and it won't readily accept the free electrons. To show this, we'll put a piece of tape at the end of the tube. Now, the electrons at the end of the wire have nowhere to go. Even if we push against the electrons in the wire, they still won't budge. To fix this, we need to connect the other end of the wire to a place where the electrons want to go, and the positive end of the battery will happily accept the electrons. In fact, don't try this with a real battery. There is nothing slowing down or restricting the flow of electrons, which results in tremendous amounts of energy being transformed into heat in the wire, and this could easily melt the wire insulation or start a fire. This is known as a closed circuit, as it creates a loop from one side of the energy source to the other. If we break the wire or remove it from one of the terminals, then the electrons will stop flowing. This is known as an open circuit. We've been talking about electron flow in a circuit and showing how electrons move from the negative terminal to the positive terminal. However, in electronics, we usually assign current as flowing from positive to negative, or from higher potential to lower potential. This is known as conventional current. In the mid-1700s, Benjamin Franklin theorized that positively charged objects had an excess of what he called electric fluid, and that negatively charged objects had a deficit of this fluid. Franklin noted that this fluid had a tendency to flow from positive to negative to distribute itself more evenly. It wasn't until the end of the 19th century that English physicist J.J. Thomson discovered the existence of the electron. Even though we now know that it is electrons that move inside of most circuits from low to high potential, the convention of current moving from high to low potential stuck. As a result, most current measurements are given as conventional current, which is the movement of positive charge in a circuit, and is represented by the capital letter I. Don't worry, the math still works out as long as we stick with either electron flow or conventional current. And since most electronics textbooks use conventional current, we'll go with that. We talked about making electricity do work for us, and the circuit forms the basis for all modern electronics, everything from the simple flashlight to massive supercomputers. If we made a circuit out of just a battery and a piece of wire, there's a chance we might melt that wire as the electrons move through that wire at an alarming rate and generate massive amounts of heat. In the next episode, we'll talk about the relationship between voltage and current and introduce the resistor.
Okay, so that's for the electric current, and we have type of electricity. Les voy a colocar una sopa de letras de los mismos, de estos mismos conceptos que nos estuvo platicando. Voy a poner 5 minutos para trabajar eso. Ahí se les mandó en el grupo. 5 minutos. Okay, we are going to do a review. Vamos a hacer un repaso de las palabras. Ya son como bastante constantes, si se dan cuenta las palabras. No van variando tanto. Y así siguen normalmente todo el contenido, pues solo cuando es de seguridad industrial sí cambia bastante muchas palabras nuevas, ¿verdad? Por la protección. For this one, wire. Wire, alambre, cable, wire. Flow, el flujo, ¿verdad? Electrons con E, electrons. Wire, flow, electrons. Conductors, conductores. Conductors. Battery, negative charge, positive charge, la carga negativa y la carga positiva, battery, batería, conductores, balance out, que debería de voltaje estar balanceado hacia ser cero, como dice. Balance out. Insulator, open circuit, ¿qué es el circuito abierto? ¿Era open circuit? Closed circuit, porque no lo puse por acá, circuito cerrado, y voltage, wire, flow, electrons, conductors, battery, con R, negative charge, positive charge, ahí está malo porque dice positive, ¿va? Eso no existe. Positive charge, balance out, como tiene una D de último, es así se dice, balance out, va más hacia la A, no tanto B, balance out, insulator, open circuit, voltage, que voy a grabar un audio y vamos a hacer estas palabras, ¿sí? Igual las voy a decir ahorita. Wire, flow, electrons, conductors, battery, negative charge, positive charge, balance out, más hacia la A, balance out, insulator, open circuit, voltage. Déjenme guardarlo, lo voy a poner. Wire, flow, electrons, conductors, battery, negative charge, positive charge, balance out, más hacia la A, balance out, insulator, open circuit, voltage. Ok, les voy a dar 5 minutos para grabar el audio, así lo pueden enviar.
Right, so that's the audio. Estas son las palabras. Hagamos un pequeño repaso. Wire, flow, electrons, conductors, wire, flow, electrons, conductors, battery, negative charge, positive charge, balanced out, balanced out, insulator, insulator, open circuit, and voltage, voltage. Okay. Let's take a look at the types of electricity. Los tipos de electricidad, okay?
Students, today we will learn something about electricity. Now, what is electricity?
That's good.
Do you recognize the person you see on your screen? Yes, he is the great Thomas Edison. Do you know what he is known for? In 1879, he invented the first practical
Más subtítulos.
Do you recognize the person you see on your screen? Yes, he is the great Thomas Edison. Do you know what he is known for? In 1879, he invented the first practical long-lasting electric light bulb. And since then, our homes are bright even after sunset. You must be aware of the fact that lights in our homes work on electricity. However, they're not the only ones that use electricity. Our televisions, air conditioners, water heaters, fans, and so on also need electricity to function. Laser light or even small flashlights also work on electricity. Imagine a life without electricity in the world today. The discovery of electricity has helped to start a new revolution in the history of humankind. But let's just keep aside all the rhetoric talks and try to understand the real thing. I haven't really told you what the term electricity means. Well, there are basically two forms of electricity. One is static electricity and the other is dynamic electricity. For now, we are only interested in dynamic electricity. From the name itself, we can say that it implies moving electricity, or more precisely, moving electric charges. Now, the next question you have will be, what are electric charges? The concept of electric charges is very important in physics and it cannot be explained in a video or two. But I will still try to give you a short and to-the-point explanation of this concept. So let's begin. There are two types of electric charges. Positive, denoted by the plus sign, and negative, denoted by the minus sign. Think of magnets for a moment. We know that two like poles, that is, two north or two south poles of magnets, repel each other. And unlike poles, attract each other. Similarly, like charges, that is, two positive or two negative ones, repel each other, and unlike charges, that is, a positive and a negative one, attract each other. But what exactly is charged? Or in other words, who actually carries these charges? Well, these charges are carried by tiny particles with incredibly small mass. They're called subatomic particles. The positive charges are carried by particles called protons, while negative ones are carried by particles called electrons. There are billions and trillions of protons and electrons present in any object around us. In some objects like metals, electrons can move randomly. While in non-metals, their position is kind of fixed and hence they cannot move freely. Now, any appliance in our house, for example a tube light, works because the negatively charged electrons are moving in the wire in one direction. This unidirectional motion of electrons in a wire is also called electric current. These wires are made of metal, usually copper or aluminium, and you can understand why. But why are the charges in a wire moving in one direction? Or what makes the charges move in the wire? The charges move in one direction in the wires because of the energy supplied to them by the transformers. So the transformer supplies energy, the charges move in a wire, which in turn makes our appliances work. A flashlight by the two electric batteries. So to sum it all up, dynamic electricity is flow of electric charges through conductors like, say, a copper wire. Generally, when we talk about electricity or electric current, we mean dynamic electricity. Hence, we simply say that electricity is nothing but the flow of electric charges through a conductor. In the next video, we will learn how to light up a small torch bulb using a single electric cell. So see you there.
Okay, that's another concept of electricity. And let's move to alternate current versus direct current.
If you are looking for a video on legendary rock music, you might have found the wrong channel. On a previous ADOMS video, we looked at voltage, power, and current, and you might remember this animation. One problem with this animation is that the voltage source shown was an AC source, while the current flow was shown as DC. So let's talk about the difference between AC and DC. The letters DC stand for direct current, and it generally means the electrons flow in a single direction. AC stands for alternating current, and it means that the flow of electrons change. Now this is where things can start to get a little confusing. This is an AC voltage source, so it's both AC and voltage. What the heck? How can voltage and current be the same? Well, it turns out we tend to use AC and DC abbreviations for voltage as well as current. So in other words, AC, voltage or current, is voltage or current that changes. DC, voltage or current, is voltage or current that is steady. Okay, so let's take a little bit closer look at these two, starting with DC. Check out this AA or LR6 battery. It provides 1.5 volts. This example circuit is going to be a DC motor like you might find in a toy car. When we insert the battery into the circuit, current begins to flow in a single direction, turning the motor. If we drew a graph where the vertical axis is voltage and the horizontal axis is time, we can see that the voltage at this point stays constant. Now, since this is a battery, eventually it's going to run out of energy and its output voltage will drop. So we know that the voltage will change over time, but the polarity will stay the same. So what is polarity? Well, polarity defines the positive direction, and for a battery, the positive voltage is created from the positive terminal. So what would happen if we turn this battery around? Well, that reverses the polarity, which means the current will flow in the opposite direction as before, causing our motor to spin in the opposite direction. Okay, so let's move on to AC, and in this case we're going to use a light bulb and a North American AC socket because, well, I live in North America. Notice how the circuit behaves when we turn the switch on. Let's break down what we're seeing by using the voltage graph again. Notice how the current is flowing in one direction, and as voltage increases, the light bulb gets brighter. Once the voltage reaches its peak, current flow stays the same, but the voltage begins to drop, and the light bulb gets dimmer. Once we reach 0 volts, the voltage's polarity changes, causing current to flow in the opposite direction. And again, as the voltage gets closer to its peak, the bulb gets brighter and then dims back down. Okay, we need to define a couple of things. First is, the change from start to finish is called a cycle. The rate at which the cycle repeats is frequency. Now, frequency is measured using the unit hertz, which means cycles per second. Different parts of the world use different frequencies for their AC systems, and it can either be 50 or 60 hertz. What this means is in 1 second, the cycle will repeat itself at least 50 times. Believe it or not, incandescent bulbs are actually flashing over 50 times per second. Now, it turns out that this rate is so fast that our slow human eyes sees it as constant light. In summary, while the abbreviations for AC and DC include the word current, they can be used to describe different types of voltage and current. DC voltages do not fluctuate, while DC current flows in one direction. AC voltages change over time, and the current flow can alternate direction. If you have questions about this video, please feel free to leave comments below. For more electronics tutorials, subscribe to this channel. You can also...
Okay, so that's for the alternate current versus direct current. I'm going to put an image here. Voy a poner una imagen solo para ya terminar este tema. Creo que eso está bien. So for this, I have the waves. Tengo la forma de onda. I have the waveform that is going to be associated with the type of electricity that I'm doing, that I'm transforming. For example, this is going to include for batteries. This is going to be for batteries. Okay. Okay, for a battery. This type of direct current, because I already have charge here that is already between the plates. Ya tengo carga ahí que está entre las placas. Así que va a ser fijo. O también un transformador. En donde va a entrar a C y puede salir de C. Va a ser un voltaje fijo también. No puede ir variando. Sí hay fuentes variables de digitales para corriente directa, but I have to select in a switch like 1.5 volts, 3 volts, 6 volts. Si tengo selectores, no puede variar a como yo quiera. But for this one, aquí en lo que es la corriente alterna, ahí sí va a ir variando, ¿sí? En la onda que se produce, because of how is electricity generated. So imagine I have a turbine. I have a turbine here. Tengo una turbina donde tengo mis bobinas y tengo un magneto. For this one, si yo saco electricidad de ahí, esta generación, porque este magneto lo puedo girar, o yo giro las bobinas, por ejemplo en turbinas, ¿verdad? Y eso me va a generar ondas para ir formándose a través de ese espacio, ¿verdad? Del conductor. Ya cuando tengo 3 ondas es porque son trifásicas. Y eso es algo que ustedes estudian bastante, ¿verdad? Los motores trifásicos y cómo generar los circuitos trifásicos. Pero al final tengo 3 ondas que se están generando. ¿Ok? Mientras que acá solo tengo una fija, un voltaje fijo, que no van a ser muy altos. No pueden ser muy altos. Aquí sí pueden ser muy altos, muy altos. Hasta de 237,000 voltios. Por ejemplo, en tendidos eléctricos de alto calibre. Mientras que acá pues yo me limito a tener siempre una corriente fija, ¿sí? Y un voltaje fijo, porque viene de la batería. Acá puede ir variando incluso. ¿Okay? Y esta es la manera en que estas 2 generaciones se usan para diferentes cosas también, ¿verdad? Esto para motores, por ejemplo, para una licuadora, ¿sí? Para un generador de diésel, por ejemplo, de electricidad. Y acá pues para circuitos, para LEDs, ¿verdad? Para cosas electrónicas, porque voy a necesitar pocos. Aquí no puse uno de los voltajes más famosos, se podría decir, pero es el de 5 voltios. Este es un voltaje pues que se usa en muchas cosas. Tengo más 5, ¿verdad? Puedo tener menos 5 también. A través de pues la transformación del voltaje. Y también acá pues tengo esos picos de voltaje y cómo va a través de la onda y de los ciclos en un segundo la generación. También tengo negativo, claro, ¿verdad? Pero el negativo la verdad que casi no se usa. Sino que en cuestión de cómo se va formando para acá en el DC, pues tengo que rectificar. Sin rectificación la onda se ve así, ¿verdad? Y también se usan varias piezas para yo poder quitar la parte negativa y solo dejar la parte positiva. Ok, eso es todo por hoy, así que les puse ahí su actividad. Está, entonces, ¿qué es lo que tenemos que realizar? Los voy a escribir por acá. Tenemos las sopas de letras, audios y el PDF. Escribir las respuestas sobre el PDF. Pueden usar cualquier herramienta que ustedes quieran, Word, las capturas de pantalla, si tienen apps para editar también PDFs, no hay problema, ahí lo pueden realizar. ¿De acuerdo? Y entregamos para la noche, ¿sí? Por favor. Nos vemos en una próxima.